Quiz 3 is just over chapter 3 of the book. So it doesn't cover lecture 11 because that's where we start to get into relations. So yeah, really good question. And then we can go ahead and get started. There's not too many of you. So if you just have any questions over any topics, we can go through a lot of problems. I have all the problems from the practice quiz. If you have any questions on those, I have selected like 7 additional problems. If there's any topics you want to go over, and we can take a look at some of those as well. Or if there's any questions over the homework, we can go over those. So for the 4 of you that are here right now, if there's any questions you have, please just type them in the chat, or topics you want to cover, and we can go over them. Yes, you will be getting homework 3 scores before the quiz. We hope to have those released pretty soon. Okay, so we have like to review element-wise proofs, and then 7, 8, 9, and 12 of the homework. Any other problems anybody has? Please just put it in chat and we can kind of take a look at them. So yeah, so let's go ahead. We can go ahead and get started with problem 7 from the homework then, because that kind of covers both of those topics. It's an element-wise proof. And then we'll cover that homework there. So let me go to a blank slide here. Okay, so let's take a look at problem 7 from the homework. So we're proving this statement about sets, and we're supposed to prove that the set of n squared minus 1, where n is in the integers, intersected with the set 2m, where m is an integer, is a subset, the set 4k, where k is an integer. Right, so we're proving subsets. So how do we prove that a set is a subset of another set? What's the technique?
We define an element for the left side.
Yeah, so let's let X be an element for simplicity. I'm just going to call this set A, this set B, and this set C. Just to avoid writing too much. So let's let X be an element of A intersect B. And then to prove that this is a subset, we're going to end our proof, do all this work in the middle and conclude that X is an element of C. And once we've done that, we've proven that they're a subset. Right, so let's look at what does it mean that X is an element of A intersect B? Well, by definition of intersection, X is an element of A and X is an element of B. Just using our definitions. So what does it mean that X is an element of A? How could we rewrite?
There exists some integer such that X equals that integer squared minus 1.
Yeah, so X is equal to n squared minus 1. Yeah, for some n in Z. And we also have that X is equal to 2m for some m in C.
Can I interrupt you just for a quick question on that?
Yeah.
For those integers, since they're defined in the sets themselves, would we still need to state the domain for a quiz?
Yes, because even though I'm using the same variable here, it's not referring, and I'm just because I just picked the variable was given above. The scope of that variable is only within the braces. So this is it's kind of like you're doing your programming in, like, let's say like a for loop or something, and you've defined a variable inside of these braces. It's called n. But we can only talk about n inside these braces. Outside of these braces, we don't know what n is.
And is that same thing true for like a case? Like if you say case 1, then you define a variable, then that variable kind of only exists inside that case.
Yeah.
Okay, cool.
Yeah, if you went to another case, that variable wouldn't exist. So yes, that's why we have to specify again that these are in the domain of C. Okay, so now we've got x is equal to n squared minus 1 and x is equal to 2n. What's the approach we should take?
I would see if n on the x equals n squared minus 1, do it 2 cases, n is odd and n is even, and then see how that goes.
We could do that, but there's a little bit more straightforward path here. So the idea is we have x equal to both of these things, so we know that they're equal. So we know that n squared minus 1 is equal to 2m. Because they're both equal to x. And then if we add 1 to both sides here, we get n squared is equal to 2m plus 1. Hey, this looks like something we know. This is an odd integer. So we know now that n squared is an odd integer. If n squared is an odd integer, what do we know about n?
N should be odd.
Yeah. Yeah, so we know that n squared is an odd integer by definition. Then n is odd. So n is equal to some 2k plus 1, where k is an integer. So how does that help us? How does this help us? Well, what we can do is we can go back and we can kind of plug in for n in this x is equal to n squared minus 1 and see what we get. So we have x is equal to n squared minus 1, which is equal to 2k plus 1 squared minus 1. And that's 4k squared plus 4k plus 1 minus 1. This is 4 times k squared plus k. So that's equal to 4l, where l is equal to k squared plus k, and l is an integer. Like closure under multiplication and addition. Thus, we know that x is of the form 4 times a number. Thus, x is an element of C. So we started with x being in the intersection. We showed it's in the right-hand side. We showed it's in the set C. So thus A intersect B is a subset of C. So this problem's a little bit tricky in that we kind of had to play around with these values a little bit, and we had to kind of come up with this idea that if we can show that n squared is odd, then we can plug that in, and we will be able to get something that looks like 4 times an integer.
So at the part where we say that since n squared is odd, then we know that n is odd, would we need to show like a proof, like a side proof showing that, okay, there's a way that we know that, and we have to, like, because we can't just like assume that out of the blue.
This is a theorem and we've gone over the proof before in class. So yeah, you would, if we didn't explicitly give it to you on this problem, then
Okay.
yes.
Can I ask if the way that I approach this problem is correct? Would that be appropriate?
Yeah, sure. Yeah. How did you approach it?
So I factored n squared minus 1 and then stated that either n plus 1 is even or n minus 1 is even. And like through substitution showed that that was equal to 4 times some integer. Is that correct?
Yeah, that's fine. Yeah, so what you did is you so everybody's okay. Let's go to another page here. So what you said is you said that like n squared minus 1 is n plus 1 and n minus 1. And
Yeah.
then you said you looked at cases. So either both of these are even or both of them are odd.
So
that
I
what was-
said that either n plus 1 is even or n minus 1 is even, but maybe that's not correct.
And that's not quite correct. We can't say that either one of these has to be even. And let me give an example. So let's let n equal 2. Just as an example, if we plug into here, we'll have 3 times 1. Both of these are odd.
Oh, sorry, I meant oh, I see what you're saying. Right, that makes sense.
Yeah, because these n plus 1 and n minus 1, these are 2 away from each other. Then the cases wouldn't be that either one of them is even. The case would be that both are odd or both are even. And then maybe in this way you could show that you could play, but you at some point you'd still, I guess what you could use, and actually we actually know which case we're in, because if we go back to the previous slide, we also know that x is equal to 2m, so x is even. And we know that this is equal to 2m. And so we can rule out that they're both odd, because an odd times an odd is odd. So we could rule out this case and then say we know that both of those are even. N plus 1 is even and n minus 1 is even.
Okay,
And
actually,
then,
I think that is what I said. I said that x has a factor of 2. And then that would imply what you're saying, right?
yes, because x is even and it's equal to this. So we know that n plus 1 is even and n minus 1 is even. Yeah, that's a perfectly valid way to prove it as well. Good question.
Thank you.
What? Sorry, you can read that. 1 second.
Yeah, so it looks like somebody wants to go over partitions. So since we kind of have more people here now, I'm just going to send out a really quick poll. So just it tries to ask what areas we'd kind of like to cover. So we've got practice quiz questions, homework questions, and then I have some additional problems that you haven't seen yet in the class that we could discuss as well. And then just some of the topics that you would like to cover as well. And we can kind of just go based on majority, since it looks like 10 people here. So let's give you a little bit more time. It looks like there's 2 that haven't finished it. So if you just want to quickly put in your vote for what you want to cover, and then we can go over it. Okay, so I'll end the poll. I'll give you like 15 seconds, and then I'll just go ahead and end it. Okay, So it looks like about like a third want to do practice quiz, half want to do homework, and then 3/4 want to do the additional practice questions. So we can start there. And it looks like there's kind of a three-way tie among the things we want to look at. So we want to look at element-wise proofs, partitions, and then descriptions of sets like set builder, notation, etc. So let's take some element-wise proofs that you haven't yet seen before. So which one is a good one to take a look at? So let's take a look at this problem. So here we've got element-wise proof. And we're asked to prove that if A intersect B is equal to A, then A complement union B is the universal set. So how do we start this problem? We're asked to prove this. What's the first step? We've got an if-then proof. So first step, right, is we assume our hypothesis. Assume that A, we've got some set A intersected with B is equal to A. So that's our assumption, right? And then based on this assumption, we hopefully can conclude after doing a bunch of work that thus A complement union B is equal to the universal set. And then we've got an element-wise proof. So how do we start an element-wise proof here? Or I guess maybe before that, how do we prove two sets are equal to each other?
So we'll need to say that A intersect B is the subset of A, and then the second case would be that, or the second claim is that A is a subset of A intersect B.
You're correct in the way that we could prove that those two sets are equal. We prove that they're both subsets, but this is our assumption, right? We've got this if-then proof. If A intersect equals A, then this holds.
Okay.
So in this problem, this is just our assumption. We get this for free, right? We're assuming the fact that we have two sets and A intersect B is equal to A. What we're asked to prove is if we know this, can we prove that A intersect B is equal to the universal set? So what we want, kind of like you described, for proving that two sets are equal, then we have two cases. So we need to prove A complement union B is a subset of the universal set, and the universal set is a subset of A complement union B. And if we can prove those two statements, then we can prove that A complement B, or A complement union B, is the universal set. So let's take a look at this first case. Case 1. Let's prove that A union B is a subset A complement union B is a subset of the universal set. So how do we start this proof? This case.
Well, could we prove that B is a subset of A from the original implication? I'm just not sure how we'd mathematically represent that.
Could we prove that B is a subset of A?
Well, I mean, sorry, B contains A. A is contained in B. Because
A would be contained. Yeah, I believe we could, but that would be. I'm not sure how we could use that necessarily later. Any other ideas? What's the kind of straightforward technique we would start with here?
Let X in A complement union B.
Yeah, let X be an element of A complement union B. And we need to show that X is in the universal set. Well, if X is an element of A union B, then X is in the universal set by definition. Of the universal set, because the universal set contains everything. So this direction, pretty easy. Basically, we just have to know the definition of the universal set, that it contains everything. So as if you've got some element that's in some set, it's got to be in the universal set. So know that this is the subset of the universal set. Now we have to go the other direction. So case 2 will prove that the universal set is a subset of A complement union B. So we start off the same way. Let X be an element of the universal set. Does anyone have any idea what can we do here? Or maybe is there a way we can break up maybe more cases that we could kind of look at?
Either X is.
You go, David.
No, you got it.
Okay, sorry about that. I was thinking we set the universal set equal to A union A complement, and then use cases with that.
Perfect. Yeah, we know. We know that A complement union A is equal to U, so we have two cases. So case 1 here is we're going to let X be an element, let's say, of A complement. So if X is an element of A complement, what do we know? Or what will be our next step to show that it's in A complement union B?
Definition of union.
Yeah. So by definition of union, we directly can conclude that X is an element of A complement union B. Because union is just as long as X is an element of one of the things, it's in the union of them. So that case is done. Now case 2, X is an element of A. So what's our next approach here? Next step we could do. So let's take a look at our assumption. If we know that X is an A, and we know that A is equal to A complement B, then we know that X is an element of A complement B. Right by our assumption. And then by the definition of intersection, then X is an element of A, and X is an element of B, which we already knew that X is an element of A. So X is an element of B. By definition of union, since X is an element in B, then X is an element of A complement union B. Now we've covered both of these cases in this second case. So thus, U is the universal set is a subset of A complement union B. Therefore, since we've shown all cases, A complement union B is equal to the universal set. Any questions on this problem?
Would we have to quote a part of theorem 6 to say that A complement union A equals A universal? Sorry. In case 2, where we say A complement union A equals universal.
Yeah, you could cite theorem 6 for this. I'm trying to think. I think we can also conclude this just from the definition of the complement. So we could do that as well. But yeah, theorem 6 would work for this. The one thing, I mean, I guess I should say, I guess I believe we can conclude this just directly from the complement, and that would be a little better approach. Because we're doing an element-wise proof, we don't want to be citing, we don't want to get comfortable citing theorem 6, right? Because theorem 6 lets us do a lot of these proofs just more directly, because it gives us the distributive property and all these other properties, and that's not what we want to do when we're doing element-wise proofs, because we just want to be talking about the element X and then concluding that it's in these different sets. So I think we could use the definition of complement here and conclude that. Awesome. Yeah, really good question there. All right, so if there's no other questions, we can jump to the next topic. So we can do, let's take a look at maybe descriptions of sets. That's kind of the next topic people wanted to cover. So here's just a small problem here. So we're writing each of these sets in just like a set builder notation. So how could we write A as a set builder notation? We have here just R of 2, right? 2, 4, 8, 16, 32, 64. So does anyone have an idea for a set builder notation? What we can do?
The set of all 2 to the n such that n is contained in the natural numbers.
The set of all, yeah, so 2 to the n, where n is an element of the naturals.
Wouldn't it be positive integers since we start with 2?
Yeah, so in this case, if we're defining it like this, yes, it would be the positive integers. Why? Because 2 to the 0 is equal to 1, and 1's not in the set A.
But one question I have about that is like a set, since it's not like by definition ordered, how do we know that like after 64 there could technically be like a 0 or a 1? So just because like the order of it is kind of convenient for our sake so that we can kind of guess the set builder notation, does it necessarily need to just include the positive integers?
That's fair. That's a really good point. That's a really good point, right? Like this is, maybe we could say this is an ill-formatted question, or it could be maybe more descriptive because we're kind of using this assumption that yeah, these elements are ordered. So let's assume that. Are ordered and the pattern continues. Right, we didn't just introduce, you know, it doesn't go like 65, 66, 67 or something weird. And that's the assumption that we make, and that's what when you take a look at the first chapter of the book, that's kind of what we're using as well when we're just introducing these ideas of sets. Because without any of these assumptions, it's impossible for us to construct examples where you'd have to use like a set builder notation unless we just have an infinite set. And that's kind of why we do this. I guess let's take a look at this. How could we do? Let's maybe change this problem. It'll make it really strict. How could we do the set? A set builder notation for this set.
Would be the set of all 3 times n such that n is contained in the integers.
Oh, yes. For B, yeah, we can finish this. Yeah, so 3 n, where do you say n is in the integers?
Yeah, n's in the integers.
Yeah, that's perfect.
Sorry, I thought we moved on to B. My bad.
Oh, no, you're perfect. Yeah, so that's correct for this one. We've just got multiples of 3. But one thing I'll just mention with set builder notation, make sure that the elements you're putting into the set are on the left side, kind of like we've gone over, and then you're referring to whatever your variables are here. Some students have also asked if this is okay. Free n, which is in the integers, and then we define n to be in the integers. This is also acceptable. Here we're just kind of, there's this additional specification that, hey, we know that this left side is going to be an integer, which works in it. And for example, it's the same, would be the same set as if we did like this. Would also be acceptable. We're just adding an additional specifier here that we know whatever thing we're putting in comes from like the necklace or something. But it's unneeded. But the book adds it sometimes. So if you want to add it as well, that's perfectly fine. But both of these are perfect answers as well. But let's take a look at a different question. Let's do a set builder notation for 2, 4, 8, 16, 32, 64. So just this set with 6 elements. How could we do a set builder notation here?
Set of all 2 to the n such that n is contained in the set 1, 2, 3, 4, 5, 6.
Yeah, that's perfect.
Could we
That
all?
is-
I'm sorry. Go ahead.
Oh, go ahead.
I was just going to ask. This might be cheeky, but could we just say n such that n is in that set that you gave, since it's finite?
I mean, I guess you could. So, like, you know, it wouldn't be a very illustrative example of a set builder notation, but surely we could do something, you know, n where n is an element of. You know, not very enlightening, and adding a lot of extra work. But yes, this would be correct. And now you can probably see that we could, you know, do set builder notation all the way down. We could kind of have fun and rewrite this using the same recursive formula, and you know, just go all the way down.
Turtles.
Yes, turtles all the way down. So another way we could rewrite this as well is we could do, say, the set of all 2n, where n is an integer, and n is greater than 0 and less than 6. Would also be a valid way. So yeah, lots of ways to do this. And yeah, maybe this problem with these finite sets would be a little bit more, yeah, less ill-conditioned. Were there any other questions on these kind of like descriptions of sets? I kind of put it as a vague term just to capture more, but were there more questions that people had? Like, did we want to look at, say, like the power set of sets, or intersections, cross products, etc.?
I guess going along with the set builder notation, do you have any tips for? I remember I'm trying to find it in the homework. There was one that was kind of a difficult
Yes.
set to find. Was it part? Oh yeah, part B of number 3.
Yeah, that one was a bit difficult. We can take a look at it really quick. Yeah, so the tips here are with this type of problem, we're really kind of going back to what we learned in kind of chapter 1 a little bit, and just applying it to kind of this idea of a set builder notation. So if you'll remember in chapter 1, we learned about, you know, how to construct closed forms for different sequences. And that's kind of what you're asked to do here. If you can find the closed form for the sequence, then you just kind of stick that in a set the right way, think about what your domain is, and then you have your set builder notation. The trick with these is often to look at kind of how the values grow. So like, for example, the difference between these two is 4. The difference here is 6, 8, 10, 12, and then knowing how some of the common patterns go. So like, for example, for exponentials, you have 1, 2, 4, 8, 16, 32, etc. So we grow by 1, by 2, by 4, by 8, by 16. So if the number you're growing is kind of growing exponentially quite larger each time, so there's some kind of product or extra factor out here, you're in an exponential territory. So you should look at 2 to the n, 3 to the n, 4 to the n, etc., etc. If, however, you are like ours, where you're adding a term each time, so we've got 4 plus 2 gives us 6, 6 plus 2 gives us 8, 8 plus 2, etc. You're growing something like n squared, n cubed, n to the 4th, etc. And so n squared, we've got 1, 4, 9, 16, 25. And this is growing by 3, by 5, by 7, by 9. So these are growing by 2 each time, right? 3 plus 2 is 5, 5 plus 2 is 7. And so we can match the same kind of growth rate here. So we know that this term has a square in it. Then we just have to figure out whatever the constant factor is as well. And if you play around a little bit, you'll discover, and one of the ways to do that is to kind of look at how the values change each time. So to find the constant pattern, so we know we're looking with a square, but what are the extra factors we're adding? So if we've got 2, 6, 12, 20, 30, and 1, 4, 9, 16, 25, the difference between these two is 1. This is 2, this is 3, this is 4, this is 5. So we know we're looking at something like an n squared plus n. And then you just have to figure out the correct domain. And in this case, we would be over the positive integers. So we'd have a closed form like this, n squared plus n, where n is in b plus. Really good question. This one is probably a bit too difficult for an exam. This is a pretty difficult pattern to discover. Somebody else said that they couldn't find the pattern for 3a. I can find one. Yeah, 3 to the k plus 2 is correct. And because for when you plug in 0, you'll get 3. When you plug in 1, you'll end up with 5. So good question.
Hey, James, on these, I'm noticing that the pre-recorded videos that we watched, they had the domain, like x is an element of the positive integers, coming before the colon, and then the rule, like the predicate, was after. So that's what I did for my assignment. And then, but I guess for the upcoming test, is there like do we need to make sure that we do it with the predicate first and the domain second?
Yeah, that was kind of what I was describing before. So could you give me like an example of one of the pre-recorded lectures that you're looking at, and we can take a look?
I just took notes on it, and I just have that, like, I just put domain colon predicate, and then one of the examples was like x is an element of the natural numbers colon x equals 2k, where k is an element of the natural numbers.
Yeah, this is a really good question. And if you'll notice here that this actually kind of follows, this is what I was describing earlier. This set is equivalent to this set, the set x, where x is equal to 2k, where k is in the naturals. So you can optionally specify that you're adding elements. The elements you're adding come from the naturals, but you don't necessarily have to. And this one could also be rewritten as this. We could just have that this is the set of 2k, where k is the naturals. We could also specify that 2k is an element of n, where k is in the naturals. These are all equivalent. And all are valid. just different formatting. So here, like at the top one, we're saying we're putting x in as long as x is an even number, right? 2 times is as long as x is of this form. Then we just kind of shorten it with this one, where we already know that x is a natural number here because it's 2 times a natural. And then here we can shorten it even further rather than getting rid of this x here. We can just say we're putting all the 2k plus the integers of the form 2k, where k is a natural. Are there any questions here? Does this help clarify? There's a lot of different ways to write sets, unfortunately. Pick whichever is easiest for you.
Thanks.
Yeah, no problem. All right, so there was the other topic people really wanted to go over was partitions. I don't have an extra partition problem, but we can take a look at the one from the practice quiz and kind of go over what we need to do for partitions. So let's take a look at this problem. This is just on the practice quiz. So we've got this set A, this set B, and this set C. We're going to show that AB is a partition of C. This is a little bit different than some of the problems we've been doing and some of the problems in the homework, where we're partitioning the set of integers. Here we're partitioning some other set that's not the set of integers. Right, so what are the 3 things we have to prove if we're going to prove something is a partition? Anyone remember what are the 3 things we have to show a partition?
The first one is the partitioning sets, the sets that are a part of the partition are non-empty.
Yeah, so first you need to show that AB are non-empty. Then second, we have to prove that A intersect B is the empty set, so everything is disjoint. And then the third thing is we have to prove that the union is equal to the whole set. And these are kind of the 3 things that we have to prove whenever we're doing a partition problem. Okay, so how do we show that AB here are non-empty? Well, we can just show that there's some element in it, so let's just pick. So 3 is an element of, 3 is an element of A, and 7 is an element of B. So they're non-empty. Right, because 8 times 0 plus 3 is 3, and 8 times 0 plus 7 is 7. So we found 2 elements in the set. So these are non-empty sets. Next, we need to show that A intersect B is equal to the empty set. So how do we prove that 2 sets are disjoint? What's kind of the technique?
So you do like an element-wise proof where you say that for every element X that is an element of A, X is not an element of B.
So you're saying assume that there's an X in A that's not in B?
So you assume that there's an X in A, and then you go through and show that that X is not in B.
That doesn't quite work. That just
the definition of the empty set is that for every element X in A, that element X is not in B.
Yes, so it's a for all proof. So you can't just pick an element in it. Like, well, I guess, okay. Yeah, that works. Yes, we can definitely do it that way. Sorry, I was a little confused. But yes, we could start with some element in A.
Well, what's the way you would do it? Because that's probably easier than the way I would do it.
I think that way does work. Definitely does work. It's a little bit harder in this case because we've got something of AK plus 3. Well, I guess it's that worked perfectly good as well. and we can quickly walk through it. So let's let x be an element of A. So then x is equal to 8k plus 3. And then we would do some sort of argument using the division theorem. And then we could conclude using the division theorem that x is not of the form 8m plus 7. Because the division theorem guarantees that there's a unique representation of any integer in this form. And so we could use an argument like that. But the one thing to note is that argument will not work if we're not doing partitions of integers. Or if let's say we're partitioning the rationals, now we can't use the division theorem as kind of a crutch to prove that these are kind of disjoint. So that would be the approach, and that would work perfectly well. And use the division theorem, conclude that x is equal to 8k plus 3, and that's a unique form, so it can't be equal to 8m plus 7. Thus, x is not an element of B, so they're disjoint. But that'll only work some of the time, depending on your set and whether or not you can apply the division theorem. What we could do, and David suggested it, is we could also show this by contradiction. So let's do that. This will always work for any set. However, though, if you're on a testing environment and you can use the division theorem or something to shorten some of these, you're more than welcome to. But since we're reviewing for stuff, I just want to make sure we know kind of a general case in case it looks a little bit different. Or you're asked to prove a different problem with sets containing rationals are disjoint, as I believe you had to do in one of the homework problems. So let's assume by contradiction that x is an element that A intersects B is not equal to the empty set. What does that mean? There's an element in A intersects B. So then x is an element of A intersects B. Or let's just let x be some element. So then x is equal to 8k plus 3, and x is equal to 8m plus 7, where k and are in integers. And then we do kind of the technique that we went through with an earlier proof. We've got two things that are equal. Let's set them equal. 8k plus 3 is equal to 8m plus 7. And then now we're just going to search for a contradiction. So we've got like 8k is equal to 8m plus 4. Yeah, here's the contradiction. We can't, and let's move everything that's multiple of 8 on the left side. So where's our contradiction coming from here? Well, this side's a multiple of 8, this side's a multiple of 4. Not every multiple of 4 is also a multiple of 8. So we're going to arrive at a contradiction here. So we can kind of factor this out. This is 8 times k minus m is equal to 4. So k minus m is equal to a half. And we know, and this is an easy contradiction. Right, since m and m, or since k and m are integers. Thus, A intersect B is equal to the empty set. Any questions here? Awesome. Yeah, so this type of argument will work for any set. So if you're like in doubt, or we're talking about rationals or some other sets, and you need to prove that it's disjoint, this type of contradiction argument will always work. It'll just be some different contradiction that you'll arrive once you set them equal to each other. If you can use the division theorem, like there's like a problem in the homework where the division theorem is easily applied to the set of integers, where you had a set of there was like a set of 2m of 4k plus 1, and you had like a set, I'm shortening this, and then there was like a set of 4k plus 3. And you need to prove that all 3 of these are disjoint. Then an argument from the division theorem works, where you can show that each element only ends up in in one set, where you break up like your cases based on the division theorem. And then you could show that these are all disjoint based on the division theorem gives you a unique representation. And then, okay, so we've done disjoint for this problem. Now we need to do, we need to prove that their union is equal to C. So what's the technique that we could use to show that A union B is equal to C? So one way, right, is we could prove that to prove that two sets are equal to each other, we just have to prove that they're both subsets. So we could prove that A union B is a subset of C, and C is a subset of A union B. And if we do both of these proofs, then we'll be able to prove that that these two sets are equal. Alternatively, we could also, in this case, we could use the division theorem, and we could take a look at let me think about how we could finish this. Actually, I'm not sure we could use a division theorem here. It would be a little bit because we're not partitioning a set of integers. It might be a little bit complicated. Could you for this particular problem?
Be contained in C, and then X would be equal to 4n plus 3, and then you would apply the division theorem and look at all the cases that the division theorem states are dividing by 8, and then rule out all of them except for the ones on the left that define A and B.
Yes, we could. It would be a long proof, but yes, we could do that. I was just trying to think if there was yes, that would work. So I'm not sure we could apply that on this problem directly. This problem would probably be quicker to prove A union B is a subset of C and C is a subset of A union B. But if you want to see some of the arguments with the division theorem, just because we're running out of time, and I want to make sure that we could cover any last minute questions if there were any. If you take a look at the examples, I believe they're in section 3.2. Yeah, so if you take a look at, like, say, problem 5, an example in section 3.2, that one would, or I guess problem 9 or in the book, they do some arguments with the division theorem as well, if you kind of want to see that technique. It wouldn't directly apply here because we're not partitioning the set of integers, but if you are partitioning the set of integers, division theorem can really help with some of these partition arguments. So I'll just leave this proof, this A and B subset of C and C is the subset of A and B, because it's a little bit too long and I don't think we can get to it all. But we have 5 minutes left. Are there any other questions, like last minute questions that we can go over that any of you have?
Since we've proven in part 2 that A intersect B is the empty set, maybe this isn't right, but do we really need to prove both of those parts for the third part, or do we just need to show that every element of C is also an element of A intersect B, or A union B? In our notes, we wrote that we just need to show that. Well, we didn't say just. We wrote that every element of C is an element of the union of the partition. sets. But do we need to show both of those maybe still?
Let me think about it. I believe, well, because what we're proving is we're proving that the union of them is just needs to be strictly equal to the set C. So it definitely can't be that the set C contains anything extra. Yes, we do have to prove both, and I'll explain why. So let's for example, so let's say we're partitioning like in this case, let's say we're partitioning a set 1, 2, 3, and A is equal to 1, the set containing 1, and B is the set containing 2. And we're trying to partition this space. We certainly need to show that there's not some extra element in C that we missed with our partition. That we missed. We need to show that there's, not every element of C is in A or B. So we certainly need to show that case, right? Otherwise, the A union B is not a partition of C. The other issue is where you get into this case. Let's say that A contains 1, 2. B contains, let's say 3, 4, and we're partitioning the set 1, 2, 3 again. Well, this is the left, they're not empty, right? A intersect B is the empty set, but A union B is not equal to C, right? Every element of C is in A or B, but it's not the other way around. So this is not a partition because the union of them is not strictly equal. So these two cases are why we have to, why we would have to kind of go both directions.
Thanks.
Yeah. Though, though the problems that you can apply the division theorem on, like when we're partitioning the set of integers, as we've done in kind of some of our examples, then the division theorem lets us short in this into just kind of one case, because the division theorem itself is a way to partition the set of integers. So, like on the homework, we had, I just get the blank page. We were looking at elements of the form 2m, 4k plus 1, and 4k plus 2, or 4k plus 3. We could use the division theorem, and say by the division theorem there, every element X is of the form 4k, 4k plus 1, 4k plus 2, or 4k plus 3, and this is a unique representation. And since the division theorem is telling us every integer can be of this form, then we just have to break down the cases. So this 2 can go into the set containing 2m, right? This goes into the set containing 4k plus 1, and then this would go into the set containing 4k plus 3. And then using just this division theorem argument, because the division theorem guarantees, since in the homework problem, we are partitioning Z, then this type of argument works, because the division theorem itself can help partition Z, and then we just had to show that each element belonged to one of those sets. And in this case, this is kind of why, if we apply the division theorem, it's kind of like one direction, but that's because the division theorem itself is partitioning kind of the space for us and guarantees uniqueness. But like in this problem, because we didn't quite have that, thus we had to show kind of both directions. Awesome. So can you show how C is a subset of A union B from the last problem? Yeah, I can kind of talk about it. It's a little bit lengthy of a proof, but the basic idea for that, to show that C is a subset of A union B, we let there be some element in C. So there's some element of the form 4n plus 3. So you'd let there be some element of the form 4n plus 3, and then to show that it's of the form 8k plus 3 or 8n plus 7, you break up into the cases. So n is even, or n is odd. And then in one case, you'll show it's of the form 8n plus 3 when it's even. And when it's odd, you'll show it's of the form 8m plus 7. And that's how you do the subset. Awesome. Any last minute questions? Again, there'll be a review session tomorrow during Nancy's office hours. So if you have more questions, I'll show up to that one as well.
Cool. Thank you.
Yeah, of course.
Thanks, James.
Yeah.
Thanks.
Mhm.